Landing a heavy commercial jet requires shedding an immense amount of velocity in a very short distance, transforming a massive kinetic energy profile into a manageable thermodynamic load. We define this challenge using the formula for kinetic energy, EK equals 1/2 mv squared, 1/2 mass times velocity squared. Because velocity is squared, small increases in landing speed result in an exponentially larger energy load that the aircraft must absorb. During a standard landing rollout, the aircraft has roughly 30 seconds to convert 100% of that kinetic energy into heat. Unlike automotive brakes, which rely on continuous airflow to shed heat over time, aircraft brakes are housed inside deep and closed wheel wells. This prevents the system from instantly dissipating heat to the surrounding environment. Aviation engineers design these brakes as massive structural heat sinks, built specifically to capture and survive extreme thermal loads that cannot be immediately released. The Boeing 737 provides a helpful baseline for commercial aviation mass and speed. A typical 737 approaches the runway with a mass of roughly 144,000 pounds, landing at around 150 miles per hour. Contrast that with the Boeing 777-9, which represents the extreme upper limit of commercial widebody mass. Fully loaded, a 777-9 has a maximum takeoff weight of 775,000 pounds and can reach speeds of 190 knots on the runway. This chart compares the total kinetic energy outputs of these two aircraft side by side. The 737 generates about 145 megajoules of energy, but the 777-9's load exceeds 1.6 gigajoules. Scaling an aircraft to this size requires a specialized thermodynamic architecture. Simply increasing the size of traditional brake components is insufficient to handle the exponential energy spike. The first constraint engineers face is spatial. All of the braking force required to stop the aircraft must be generated entirely within the narrow internal diameter of the wheel rim. To maximize friction surface area within this confined space, heavy transport aircraft use a multi-disc architecture. Half of these discs are called stators. They are keyed directly to the fixed, non-rotating axle tube. The other half are rotors. They slide into the gaps between the stators and are keyed to the spinning outer wheel rim. Aircraft hydraulic systems deliver 3,000 pounds per square inch of pressure, firing pistons that compress this entire stack simultaneously. This alternating configuration multiplies the friction surface area by orders of magnitude. It provides the necessary mechanical clamping force without increasing the landing gear's overall footprint. Generating that much friction produces extreme heat. High-carbon alloy steel melts at 2,000 degrees Celsius and begins to warp and lose structural integrity under heavy loads well before reaching that point. To handle the loads of heavy transport aircraft, engineers moved away from steel entirely, developing carbon-carbon composites. This table compares the thermal properties of high-carbon steel against carbon-carbon composites. As the maximum service temperature row highlights, carbon-carbon maintains its structural integrity and a stable friction coefficient at temperatures up to 3,000 degrees Celsius or 5,400 degrees Fahrenheit. Achieving these properties requires a complex manufacturing process. The discs undergo months of chemical vapor deposition, where free carbon atoms deposit into a porous fiber preform, followed by a double firing sequence to reach the final density. These composites function as highly efficient structural heat sinks, performing optimally at the extreme temperatures generated during a landing rollout. Applying 3,000 psi of hydraulic pressure instantly to those carbon discs creates a problem. It locks the wheel. This induces a skid, which destroys the stopping distance and blows the tire. This chart illustrates the Mu slip curve. To stop efficiently, the tire must operate precisely at its peak traction point, right before it loses grip. Rotary transducers in the wheel axle continuously measure the deceleration of the wheel, feeding wheel speed data directly to a digital anti-skid control unit. Based on that data, the control unit modulates the hydraulic pressure on and off up to 15 times per second, keeping the tire exactly at that optimal slip threshold. The mechanical power of a multi-disc carbon brake is useless on its own. It requires this microsecond digital modulation to translate raw brute force into actual controlled deceleration. The ultimate test for this hardware is a rejected takeoff, or RTO. This is an emergency maneuver where the crew aborts the flight at V1, decision speed, the absolute last moment before the aircraft commits to taking off. Under FAA Certification Standard Part 25.735, manufacturers must prove their aircraft can survive this exact scenario under absolute worst-case conditions. First, the aircraft must be loaded to its maximum takeoff weight. Second, the engine thrust reversers are entirely disabled, forcing the wheels to handle the stop alone. Finally, the brake discs themselves must be machined down to a 100% worn state, leaving only 10% of their original usable material. Worn brakes possess the lowest possible thermal mass. This ensures they will reach the highest possible peak temperatures during the test. These regulations intentionally strip away every safety margin and aerodynamic aid. They force the wheel brakes to single-handedly absorb a kinetic energy load that would otherwise be fatal. For the Boeing 7779, this means a 775,000-pound aircraft slamming its brakes at 190 knots. The energy conversion is immediate. The brakes are subjected to over 1 billion foot-pounds of torque in a matter of seconds. They convert the kinetic energy into heat so rapidly that the carbon discs glow bright red, with core temperatures exceeding 2,500 degrees Fahrenheit, or 1,370 degrees Celsius. That is hot enough to liquefy aluminum and destroy standard industrial alloys. Successfully passing the RTO event proves that the carbon-carbon composite architecture can reach thermal overload without shattering. It maintains its structural integrity while bringing the aircraft to a complete halt. Once the aircraft stops, the danger is not over. The massive amount of heat stored in the carbon discs begins transferring outward into the surrounding wheel assembly. This rapidly increases the pressure of the nitrogen inside the tires, creating the severe risk of a catastrophic wheel explosion. To manage this final thermal threat, engineers embed eutectic fusible plugs directly into the wheel rims. The core of the plug is manufactured with a specific engineered melting point, typically around 177 degrees Celsius. When the outward heat transfer hits that threshold, the plug melts. This allows the highly pressurized nitrogen to vent safely into the atmosphere, deliberately deflating the tires so they cannot explode. The aircraft is now completely immobilized on the runway for hours, resting on flat tires and glowing carbon brakes. This grounded aircraft represents a triumph of extreme engineering. The system executed exactly as designed, sacrificing its own components to safely absorb and dissipate a lethal amount of energy, saving the airframe and everyone on board.